Localized air extraction, we touched upon it. Again, identify some areas that are suitable for localized air extraction. I was at one of the facilities in Peterborough where the facility had every single CNC machine had a localized air exhaust. And they even if it was localized, it wasn't exhausted outside. They put it through the filter, and that air was reused again. Says how effective existing hood systems are. Many of you have hood systems that are completely ineffective because they got gunked up years ago and nobody cares. Because it's much easier, somebody complains about the fumes, it's much easier to put another fan on top of the guy than actually investigate the issue. I had on the same, in the same facility, we had a quench line. When we made a coil to put it to quench, we had a localized fume exhaust. At least 3-4 times a year, we had a local fire in the chimney, because that was all oil that got pulled by the fan, and eventually, if it wasn't cleaned, it started a fire. So that was our signal. Let's clean the chimney. But if you don't have such an environment, the chimney will get clogged up. You will not get good extraction out of the hood, and you will think you need extra exhaust on the roof. And assess the feasibility of filtering that extracted air and keeping it in the building. These systems can be expensive, so it's not for everybody, but potential is there to be explored. If your air is specifically, there is some need for a specific air quality, this might be a cheaper way than going through the whole fresh air cycle. Talk about air curtains. That's another way of reduction. Reduce the building envelope losses. We all know building envelope losses that you either have too much air going through your shipping doors, too much air going out of your shipping doors, windows, any other example. On the door, shipping door, for example, there's lots of air infiltration usually because you have negative air. So what people do is they will install air curtain, which is nothing more than a fan that takes the indoor air, blows it down in a fairly narrow stream of air, and that shuts down your infiltration through the door. That's how air curtains work. Right? So it could be a fairly good idea for some of the people. The other one is shipping door seals. Doors are usually bigger than the truck outline, so you have a gap around it. And if you don't have that seal, you will have infiltration of the air around the truck every time the truck is parked there. There's a calculation here that I won't dwell on because we have a web portal that you can go online. You can calculate the air door infiltration, rapid door, dock seal. You can do all of that right on the website. But just to give you an idea, it matters where your door is situated. If you look at the bottom table, north, northeast, east, direction of the door, and then you see the speed of wind, which is corrected for that orientation for GTA area, it's significantly lower than your typical average wind in the Toronto area. So it matters which way your door faces. But all of that is accounted for in our calculator. All you have to put is the size of your door, where it's oriented towards, and it will calculate this for you. If you have 1 door, 2 doors, 5 doors, and otherwise you cannot reduce your exhaust environment, so you cannot change the balance of your building in other ways, then air curtain can help. If you have hundreds of doors, now you get into all sorts of interactions, especially if those doors are like cross-dock doors on one on the other side, or if they're all around the building, it can get pretty tricky. I wouldn't take this calculator, multiply it by 100, and say, this is my savings. I would be very leery of that. Because there will be interactions, and we had cases where if you apply that logic and you apply that calculation, you will save more than your entire building is using. So we want to be a little sensitive to that. So that's one of the things that would be. 1.08 times your infiltration amount times temperature difference. Those are the savings, essentially, by stopping that infiltration. The question is, how do we stop infiltration? That's a more important question than actual amount of infiltration. And these are the things that I was just talking about, the small print on all these calculations. It's for typical application. So it's meant to be for buildings with a fairly balanced airflow. Don't do it for the buildings with high negative or positive air pressure. because that means you have other issues, and air curtain is just like putting a Band-Aid on it. And ultimately, you'll save natural gas, but you'll add cost of the electrical energy to run the fan. So you have to take all of that into account. Use judgment. Use a good engineering logic that we use for everything else. When you're buying a piece of equipment for the production, you analyze it to depth. You look at every single aspect of it. Yet you tend to buy these things as if they're on the shelf, as if they're meant for you. They're not. They're meant in general. So you have to be very careful what you're buying when you're buying it. So for dozens or hundreds of doors on the same building, I would be very careful how I apply it. Because as I said, I've seen cases, I had cases myself where if I calculated per door, and the savings will be 10 million cubic meters, they only use 3 million cubic meters to begin with. And that includes 5 of their ovens. So we have to be a little bit reasonable and judge, do a back calculation. How much energy do I use in the first place? And if I sealed all these doors, would I really save all the energy? Look at it from that perspective. So keep doors closed, ensure dock seals are installed, good working order, consider installing air curtains and rapid doors, all good, all valuable things. But maintain proper building air balance is a key. I see so many people put, they will close, like Carl said, they will close a couple of doors, or they will put infrared heaters above the doors. That's my favorite. What does infrared do? Infrared heats the floor, right? So if you have 500 cubic feet of air rushing by that infrared, you really think it's going to heat it up? No, it won't. It won't make any difference. It will have nice red bar above the door. It won't make any difference to the quality of the indoor air or the drafty environment that people see downstream. So the second of 3 R's, now that we reduced everything, is recover it. Also important, also misunderstood, because recovering energy usually implies, and people will usually try to sell you the most complex solution to recovering energy. But that's not what we meant by recover. Yes, for some it's appropriate. For some, that's the really best way of doing it. But in reality, a lot of them are low cost and simple implementation. And most of them will have a payback of less than a year, if done properly. That's what I mean by recover. So air compressors, for example, recover the waste heat of the air compressors. They're inherently inefficient energy users. 80 to 93% of your energy required to compress that air is waste heat. And there is nothing you can do about it. It's not the fault of air compressor. That's not the fault of anybody. That's just the way physics works. And most of them, to make it even worse, are placed in the separate room. Because you usually don't want warm air, because warm air makes your air compressor run even more inefficient. So you want a cold air getting into the air compressor room. So that room is usually isolated, and it's pretty noisy usually. So people don't like to have that inside the facility, unless it's a small compressor. Right? So that waste heat is not even used to heat up the space. It's total waste. What's even more funny is the people put big fans onto those rooms to get that heat out, because when the technicians go and work on it, they get all sweaty around it. So they put a fan on top of the roof. On the water-cooled systems, similar example. 50 to 60% of that heat can be recovered very easily. I had a customer, Sloba, 6 months ago? They just hooked up additional heat exchanger into their loop for cooling the compressor that went to the cooling tower. They recovered 250,000 cubic meters of gas by doing that. One heat exchanger. They didn't have to move anything. For air-cooled systems, 80 to 90% of that heat can be simply recovered by ducting that air into the room. So you have a compressor room, you put a duct. Most often you won't even need a fan in the duct, but if you need, you can put a small fan in it. You dump that air inside the building, you reduce your space heating requirements. Any sort of heat that you generate in your process, welding machine cooling loop, injection machine cooling loop, Other water stream heading to the cooling tower, for example, water-cooled compressor or something like that. Anything can be hooked up to some sort of make-up air preheat loop and takes away from energy required to heat that air. There's many, many different ways of doing it. As I said, one guy was taking just, instead of the make-up air preheat loop, he just installed additional heat exchanger, and he's preheating the water that goes into his process. He's got 27 gallons per minute of water that's being heated by 60 degrees F by that loop. That prior to that went straight up to the cooling tower. So cooling tower doesn't work as hard anymore, and he's saving energy. So the process weight heat can be a good choice in proper applications. Sometimes if you use it directly exhaust out of the process, you have to make sure it's a clean exhaust stream so it doesn't plug up your heat exchanger. Proximity of heat sink is important because if you have to take that heat and put it 500 feet away, it might impact your energy availability. And do it when all other heat recovery options are already exhausted. Properly balanced building heating costs can lead to long payback time. So if your building is well balanced, and if you have your windows closed and all that good stuff on your envelope, which most of you will have, there really isn't that much energy being used for heating the building. And it's only applicable to heating season, so you're essentially doubling the length of your payback. So my team and myself always suggest using the process heat, recovering it back into your process because it's constantly used, so your return on investment is much better that way. Which brings us to the question of internal heat gain, and we've been talking about it, touched upon it in the last one, but we never talked about it in any extent, in any detail. So we'll attempt to do that here. Please make sure that you understand this is not a comprehensive guide to internal heat gain because that's a very complex subject, especially in industrial facilities. So we'll try to attempt something that is simple enough that gives you a good idea what's going on without being professorial and having formulas and integrals done here. So if you look at how do I know my building has internal heat gain? Many people are stumped by that, but it's fairly easy to do. You do the scatter plot graph. You chart your outdoor temperature for your facility and your monthly consumption in cubic meters. And you do a scatter plot and you get something like this. And you look at it and you say, okay, my set point of the building, all my heaters are set at 21 degrees Celsius. My makeup air is set at 21 degrees Celsius. But I'm looking at this, and somewhere about 16 degrees Celsius, I'm not using heat anymore depending on the outdoor temperature. So this difference between 16 and 21 degrees Celsius, that's your internal heat gain. Even though your units are set at 21 degrees Celsius, they don't actually heat over 16 degrees Celsius because there's no usage there. So it cannot be possibly heating relative to seasonal load because that line is now straight, so that's your process load. So that's a very quick way of understanding whether you have internal heat gain or not. And it gives you an idea where that is. And it's very important because people will, when they calculate cost of exhaust or cost of makeup air, they will use 21 degrees Celsius as the temperature to heat the air to. But the reality is you only heat it to 16 degrees Celsius. So you're cheating yourself on your payback. So this is a very important part to understand. So we talked about metered seasonal load. This is essentially when you take your process load out, and this is what you pay the natural gas for, split into space heating and makeup air. In some fashion, depending on your facility, there will be lots of makeup air or little space heating, lots of space heating, little makeup air, another topic. But then there's exhausted air energy content. When you take all your exhaust and you say your building is 21 degrees Celsius, and I have 5,000 CFM getting out of the building, that 5,000 CFM at 21 degrees Celsius has a certain amount of energy. Almost always in our facilities, in our service territory, that will be larger than your seasonal load, which means you must have some internal heat gain. So if your internal heat gain is less than that exhausted energy, guess what happens? You have drafty environment, your space might not reach the set points in all the areas, so you have cold spots around the place. That's an opportunity to reduce exhaust volume. Conversely, if my internal heat gain exceeds what my exhausted energy is when I add it to the seasonal load, that means I have opportunity to redistribute that heat. It means that in some areas, my facility is really hot. In the others, maybe cold. Or it might be nicely warm everywhere, and I can reduce the set points. In either way, that's opportunity to reduce the heating set point. How many of you have had people who work next to the oven in the middle of January, walk in shorts, and the guy at the shipping door freezes? That's what we're talking about here. That's very common. So if you look at internal heat gain, how can we get an idea how much of heat there really is? I'll just give you a simple example that can be expanded. And it is simple, so it's used as a rule of thumb. But it's pretty good for what we need. So first of all, you have to understand what your control volume is. We don't include the offices. We include only a main space because this is what we're interested in here. So, for example, you'll see there the compressor room on the side there is not included because it's isolated from the rest of the space. It doesn't contribute anything. So we don't take that into account. And let's say that our facility overall has 100 kilowatt average electrical load, and it uses 100 cubic meters per hour. Rough numbers, this is made-up facility. This has nothing to do with reality. So out of 100 kilowatts, compressors, let's say, use 20, and we take that out because they're out of our control volume. Exhaust fan motors, let's say we have 5 kilowatts. We take that out of the volume because they're on the roof and they don't contribute to the heat inside the space. Let's say some other is another one. So that's 74 kilowatts inside that space that we're interested in. So if we look at that 74, now we have 90% of that will be converted into internal heat gain. Because when you really think about it, as the motor turns, as the motor works, what happens? We're overcoming the friction somewhere in the system to move something. That friction is nothing but the heat. Eventually turns into heat. So that all of that energy pretty much gets converted into heat that stays in the space, unless you have conveyor going out of the facility on the other end. As long as it's inside the facility, it gets converted into heat. Same for process gas usage. Let's say we have only one oven. We have no cooling in the oven, just have one oven. Stack losses, let's say 45% of our input energy into the unit goes up the stack, which means 55 cubic meters gets converted into something inside the facility. Whether it's radiation losses, whether it heats up the part that goes for, say, painting, it goes from 20 degrees Celsius to 350 degrees F. Right? And then we have large conveyors that will run that painted part that's warm around the facility until it cools down. Well, that's the heat that gets trapped inside the building. It may not be good, well distributed, but it's inside the building. So combined, just out of that, is about 2 million BTUs per hour. And these are very low loads for any typical facility. So we have large internal heat gains, large. So wouldn't it be a good idea to take some of that heat around the hot areas and place it somewhere where it's cold? That's what we talk about when we talk about recovery. We're not talking about a complex system. Air infiltration through the door, 3.8 degrees Celsius average winter temperature in GTA. And here we have a source of heat. Very typical. It was typical for us. We had 12 ovens of different sizes, high heat annealing ovens. It was hot as hell anytime there. But you go into the warehouse just next to it, and it was freezing cold. Right? This particular facility that we worked with had 88,000 CFM of air going out at 25 degrees Celsius. What if we minimize that exhaust? Let's cut the exhaust. Now let's put 60,000 CFM through some sort of sock and the fan on the other side of the building where it's not that hot. We drop it down. Now that volume of air will reduce infiltration, and it will keep average temperature in the room at about 18 to 20 degrees Celsius. And you haven't done anything special. You just reduce the exhaust, and you put the rest of the exhaust, and I'm not talking exhaust of the oven. I'm talking regular room exhaust above the ovens. You know, those axial fans that remove the heat that because the area is very hot? Those fans. You remove that air, and you put it back on the beginning of the building. That's way better than putting infrared heater on top of the shipping door and doing nothing else. Way better. This is the example of it. So going back to this internal heat, and some people call it free heat. Many people will ask, well, it's free, so who cares? Right? Well, sadly, it is not free. Believe it or not, you paid for it. It's just because it's a waste heat doesn't mean it's free. You paid for the energy that generated in the first place, right? So if you look at it, internal heat gain, you can equate it to basically heating up your space with a light bulb. Can it be done? Yeah. Is it efficient? No. So the first step would, going back to our reduce step, reduce whatever you can, reduce your losses. And then what you cannot reduce, because there are physical limits to what you can reduce money-wise, economically reduce, there's limit to that. Then use that to recover it. That's by no means advertisement to let's run it as inefficient as possible because we're going to generate a lot of internal free heat. Well, it's not going to be free. You will still pay for it. So first reduce, then recover that heat. So, which brings us back to the last one, replace. It's usually go-to solution. That's why I left it last, because it's easier. People, first thing they do is, my unit failed, I'm going to replace it with the exact same one. Well, let's give it a proper thought. Let's use some business case development. You use it for everything else. Why wouldn't you use it for this? And hold vendors accountable the same way. Remember, we're talking about now global competition. We're talking about everything matters. In our facility, we didn't even know when the makeup air unit was replaced because somebody's nephew had an HVAC facility who was fixing our units. We never even knew that it needed fixing. So nobody looked at it. But we had 12 ovens. We could have used all the heat from those ovens. We wouldn't need any energy to heat the space, to heat the water, do nothing. But we never did it. Facility is closed now because we were not competitive enough. We don't want that to happen to you. Why do we do it? It's least risk. If you replace something in the exact same unit, nobody's going to blame you that it was a bad decision. It was that way originally. Who cares? Right? Sometimes non-energy benefits of fighting everybody, trying to get an audit done instead of just replacing the unit will just outweigh it. And you'll say, forget it. I just don't have time to fight everybody on every single issue. I'll just give up on that one. And sometimes the choice to replace that unit is really correct one. So it's possible, right? So why did I put it last? Well, because the quick fix does not equate to the right fix every time. Just because it's quick doesn't mean it's correct. Many times replacing the equipment does not solve the underlying problems. Replacing the dock seals, it didn't solve the underlying problem of the building air. And eventually you'll have to deal with it anyways. So funds can be used to the better effect if we're better prepared, if we understand what our facility does. Right? So being prepared is to understand how your facility uses HV and why. Why do you have so much exhaust? Is it needed? Why do I have so many makeup air units? Are they all needed? Do I have hot spots? Do I have warm spots? Do I have the cold spots? Where are they? Can I satisfy all of them with that? A little bit of redistribution. So we talked about it, properly executed air balance. It will give you all of this. If it's properly done, it will measure airflow in your facility, both volume and temperature, for each individual inlet and outlet of the building. It will give you indoor air movement, smoke test, candle test. It will account for seasonal variations, so when they go and measure it in the middle of the summer, it doesn't happen that you think you have 200,000 CFM of exhaust, only for your maintenance guy later to tell you, no, we turn off 150,000 in the winter anyways. Proper air balance will find that out. It will be part of the report. And also it will take note of the existing equipment. So if you have dampers that don't close or whatever, if you don't have any dampers on the top of your fans and it could rain inside the building, they would note that. They wouldn't do anything about it, but they would make a note of it. And your influence on purchasing will increase if that air balance assessment has been done up front. So it's not something you have to do when something fails, because then usually there is no time and the funding is better spent on replacing the unit than looking at the audit. And if one of our ESC has worked with you to actually clarify the scope of work. We had a campaign last year where we paid for almost all of the cost of the air balance, but we have dictated what needs to be in the scope of work, and our customers have told us that we had much better success as to what we got at the quality of the air balance study. Because usually the people will just measure the exhaust fans and the input areas and give you the plus minus. That's not the point of air balance study. Any student can do that if you have them run around and read the nameplates. You actually need to measure it. You need to understand where it goes. This is another question we often get. Okay, so you guys are so smart. Why don't you just tell me what to do? It's not so easy. Right? Many times replacing the equipment does not solve the problem. And we need to help you understand the problem. This is not something we have, at the page 14, customer number 13 has this problem. That's not how it works. We need to work with you to understand what the problem is, to develop the solution before we can recommend something. So some guys will have great success with the infrared heaters. Some guys will absolutely hate it. Some guys will need to add makeup air units. Some guys will need to take some exhaust out. It depends on the facility. Unfortunately, industrial facilities are very complex by the nature of it. That's why when you read any literature out there on the subject of energy savings, it will usually be on commercial buildings. It will not be on industrial buildings. You truly are unique. Every one of your facilities is different. And before we can recommend something that makes sense, that we would be willing to give you, because as I said, we understand you have to go and ask for money from somebody else. And asking for money usually has some repercussions if that doesn't work out. We want those repercussions minimized and mitigated. So if there is any risk, we want to be open with you. I'm going to say, this is the risk, this is what the risk is, and then we weigh it with you. That's why we don't like recommending something just blindly and say, no, go do it. If all of you install one infrared heater, we'll all be happy family. That is not how it works. So we avoid generalities. Because what may be a good solution for Karen may not be a good solution for Victor. It's important to understand your facility, and only working with you can we do that. This is another question. Do I really need a business case? I do business case for everything else. Do I really need a business case for this? No, you don't. But then you'll end up most of the time with the wrong decision because you won't account for everything. It's not just the first cost of purchasing the unit. It's also how long it's going to last. Why did the last one fail? How much energy will it use over the lifetime of that equipment? Usually the cost of equipment is 1/10 of the overall cost of that equipment's life. So why focus on 0.1 of the overall cost without considering everything else? If you do business case, it also opens the range of possibilities. Now people get to ask questions. Now it's not just replace it with the same thing. Let's replace it because this, and this. And somebody else will say, well, why that, and that? You would be amazed what happens when you probably won't be because you were probably there in that situation. When you sit around the table and you ask something, why is it that we do it that way, and you get blank stares. Building a business case helps you find out those blank stares faster. Ultimately, it has the potential to help the bottom line by making the energy visible. Because if you build the business case, you now have to put how much that unit uses energy. So now everybody starts talking, oh, do we need to use that energy? Because what's the impact on our bottom line? And it makes purchasing decisions more objective by doing it, quantifying the benefits. And not just saying, well, it's good for environment. No, it's good for environment, and it's going to save us this much dollars. Energy benefits will depend on your current consumption. And that current consumption helps you understand where the energy is going. Is it really worth my while to worry about space heater if my space heater uses 0.01% of my overall consumption of natural gas? Maybe it's not worth my while. Maybe I can give up that fight to fight something else. And ultimately provides the list of questions you're going to ask your vendor. Instead of just saying, Joe, just give me the same one of this unit, you can ask. You can actually make a scope of work, and you can hold them accountable. So if somebody wants to sell you a piece of equipment that's going to save you 30% of your energy, you put the scope of work, and you say, It will save 30% of the energy, sign on the dotted line. Let's see how many of the vendors will sign on the dotted line. I bet you it will be pretty thin selection. But everybody will promise it. I can tell you from our experience, saving 30% of energy on anything with one stroke is a master stroke, and it doesn't happen very often. So this is our campaign for this time around. We will double the incentive for anybody who had done audit with us in the last, from January 1st, 2013 to today. And they had identified HVAC project there that you haven't done so far. If you do it by November 30th, 2014, which is before the heating season, major heating season, we will double the incentive up to $25,000. So you will have some more information in it. For those of you who have not done audit with us before, we'll offer similar what we had before, where we'll give you up to $6,000 per customer for an air balance audit. That we will be involved in the clarifying the scope of work. We can offer some names of the people who will do air balance audit, but we really don't care who does it as long as they follow the scope of work. And all of those are meant to do two things. One is we do audits on a regular basis. You do audits on a regular basis. I bet you have shelves full of audits of some sort that nobody ever looks at once it's done. So we want to double the incentive because we want to get you to actually execute some of those. They don't have to be large projects. They don't have to be major hitters. They could be, but they don't have to be. But it's still worthwhile doing, especially before the main heating season starts, because you will realize the savings over the next 6 months. So that's the idea behind those. And the other one is if you didn't do air balance audit, we understand that that's sometimes problematic to get a funding out of it. So $6,000 goes a long way. That should cover most of your air balance audits in this room. Large customers probably will have a little bit more, but average cost of the air balance study was about there, right? $4,000 to $5,000 for an average facility. Because you will realize the savings over the next 6 months. So that's the idea behind those. And the other one is if you didn't do air balance audit, we understand that that's sometimes problematic to get a funding out of it. So $6,000 goes a long way. That should cover most of your air balance audits in this room. Large customers probably will have a little bit more, but average cost of the air balance study was about there, right? $4,000 to $5,000 for an average facility. So just let's repeat this one more time, then we'll go for a brief break, and then Trevor will do some workshop examples. So reduce the losses first. Minimize the wasted heat. That's the step one. Any way you can do that, that helps. Then recover the heat. So whatever you cannot reduce, once you cannot avoid losses, capture those losses if you can. Only then, if you exhausted all of that, then replace the equipment with the new or different. Because no matter how efficient the equipment is, if you haven't done the stuff on the bottom, you will still run it inefficiently. It makes no difference, and you will not realize the savings.